All right, so I was worried because that question, all right, so don't take this wrong, but the question doesn't make sense. So come at me again with it. If the radius is 4,
yeah, and
then find the what?
Convert it to degrees.
Oh, that doesn't make any sense. I need you to understand. Radius is a length, correct?
Mm-hmm.
I could put it on a circle. You with me?
Mm-hmm.
So you'd have to tell me so many radians. How many degrees is that? So a radius is just the length from the center to the outside of the circle, correct? That's what a radius is. A radian is if I took that radius, bent it, put it on the circle, that's the angle I would go through. A radian is an angle. It is related to the physical measurement of putting radii down. Are you guys kind of with me? That's why it makes so much more sense than degrees, because it is an actual physical measurement of the circle. It's not some made up bullshit. Yes. Does that make sense? I'm sorry. Okay.
Yeah.
Okay. Yeah.
Would you technically use like pi or 80 degrees to find every other plane in radians?
Yeah, it's totally. You could change any degree you give me. I can turn it into radians. Yes.
No, but like, let's say you take like pi and then it'll be equal to 180 and you use 180 divided by 6.
So that's pi over 6, and we saw last time that's 30 degrees, right? Yeah, exactly. Yeah, exactly. So, coming right off of what you just said. There we go. If I had an angle that was, what do you got, Jeff? 135 degrees. How do I convert that to radians? In exactly the same way that we know 1 foot equals 12 inches, I know how many radians equals how many degrees. What? Tell me. How many radians equals how many degrees? Pi radians equals 180 degrees. And that's what we came out from last discussion about. And I think I got most of you guys with me, even though I sensed a near mutiny happening, but I think I got everybody kind of with me on that. Okay, maybe. So I can use pi radians as 180 degrees, the same way I use 12 inches as 1 foot to convert between the two things, right? So, go ahead. Sorry.
So when you say pi radians,
Yes?
should I leave it as RAD or do I put R? Is R representing radians?
Oh, no. We definitely don't put R for radians. That's very confusing because R is radius, right?
Okay.
So you can put rad for radians. To be really honest, if I just said, for example, in the future, I'm going to say something like this. I'm going to ask you this, and you're going to have to know it immediately. Because all it is just asking you what's the sine of 45 degrees. We don't quite know that yet, but soon you're going to remember that. If I do 180 divided by 4, I get 45 degrees. Is there any units in here?
No.
The most important thing is there any degrees? Do I see a degree in there? If I don't see a degree, it is radians. So I don't always write rad, thank God, because that would suck already everywhere. So the idea is if I don't see degrees on a number, it is radians. If it's representing an angle, are you guys with me? Yes?
So do we just put a number?
What do you mean?
Like say that's
What would this be now that you know this is 45 degrees? What's the sine of 45 degrees?
Rad 2 over 2.
Rad 2 over 2. Yeah. Don't say anything. Don't say anything. Don't say anything. Think for a minute. Don't say anything. Okay, what's that?
0.
Close. Negative 1. Because what's pi? And by the way, I really want you to understand, I know pi is 3.14. 159, blah, blah, forever. You with me? I know that. But when I'm talking about as an angle, pi radians is the same thing as 180 degrees, right? And just to really hammer home, if I have a unit circle, if I have a circle of radius 1, right? Happy little circle, right? Okay. He looks happy. If I go all the way around, how far have I gone? No, not angle. I mean actual
2 pi radians.
Yeah, I've gone 2 pi, not 2 pi radians. I've walked 2 pi. If this is 1 foot, I just walked 2 pi feet. You guys understand? And isn't that 6.28 whatever? You with me? So pi, how far would I go if I just went pi? I would go halfway. So I need this I don't want to confuse you. Please just go. If I walk pi, I get to here, correct? What angle did I just go through? That's what I mean when I say pi radians equals 180 degrees. A radian does measure the distance I walked, but it relates to the angle that I go through as I walk it. Okay, maybe. That's the connection between radians, degrees. Okay. So how do I convert this many degrees to so many radians?
Multiplied by pi over 180.
Yeah, I want to kill degrees, correct? So I'm going to put degrees down here so they cancel. See that? And I want to end up in radians. So I know that there's pi radians and 180 degrees, right? And now you just simplify that. And almost never will we multiply by pi. We're almost always going to have our radians something times some pi, right? Like pi over 4, 5 pi over 6, all that kind of stuff. You guys with me? So how would you reduce this? What goes into both of these?
45, but also, what was the other 4, right? 9. Or no, 9, yes.
9 goes in, sure. So 9 goes in 15 times, 9 goes in 20, and then 15 and 20, 5 goes into both, right? 3, 4. So this is 3 pi over 4. Now real quick, a couple of things I want to point out. If I went 135 degrees, what would the reference angle be? Draw it, don't say anything. Draw 135 degrees. What's the reference angle? Don't say anything. Draw it. Some of you guys are staring at me. Draw 135 degrees, and then figure out what the reference angle is. Don't say anything. If right now you're not sure what a reference angle is, it's bad, because that was on the last test. It's bad, okay? It's bad. All right, so if I draw 135 degrees, I end up in what quadrant? 2. Reference angle is always one of two things: how short I am, or how much I went past the x-axis. Because it's got to be a reference to the x-axis. That's why we call it a reference angle. So what would this be?
45.
45. Now watch this. This is 0. What is this in terms of radians? We know. Pi. Is that cool? What would this be in terms of radians? Yeah, 1/2 way. It's pi over 2, right? And let's check it. Pi is 180 divided by 2 is 90. That's 90 freaking degrees. Kick ass, right? So 3 pi over 4, how far short am I of a whole pi if I have 3/4 of a pi? If I have 3/4 of a pi, how much am I missing of a whole pi? 1/4 of a pi, correct? That's the freaking reference angle. Reference angle. Reference angle. Same number, right? Again, what's 180 divided by 4? 45. Good. So we're going to get to a point, in fact, I'm going to do that right now. We're going to do several examples of finding reference angles when it's written in radians. And before I do that, I want to really make sure you understand the basic angles that we have memorized stuff for. So for example, 15 degrees. Do we have anything memorized for 15 degrees? No. 30? Shit, yeah. Right? Okay. So help me out. Let's see if you guys remember. Considering pi is 180, we can build from that pretty easily. How do I make 30 degrees if I start with 180 degrees? Well, what do I divide? Here, I'm going to write 180 degrees. There, I did it. What do I divide that by to make it 30 degrees? So pi over 6 is the same thing as 30 degrees. Is that cool? Now, again, these are angles. Yeah. So pi over 6 radians. Let me go ahead and write rad there so you guys understand. If you do pi divided by 6 in your calculator, you will not get 30.
No.
But as an angle, these represent the same thing. Somebody help me out. What is pi divided by 6? 30. No. On your calculator. What is pi divided by 6? My hand doesn't have that function. Like 0.51, something out. This is as far as I can go in my head.
0.5235.
What is it, sorry?
0.5235.
What, 0.5235. If I walk 0.5235 around a circle of radius 1, I will have gone through an angle of pi over 6 radians. Okay, I might be addressing something that you aren't even concerned about, but to me, this is what is confusing, possibly, is pi over 6, if you do it in the calculator, you get this number, don't you? That if I walk this distance around a circle of radius 1, I will have gone through an angle of 30 degrees, or pi over 6 radians. Radians takes the actual physical length I've gone through and considers that as an angle. That's what it does. So that doesn't equal 30 when I throw in the calculator, unless I remember pi is 180 degrees, correct? You guys with me? And it's because that's the angle that it represents, not that's the number it is. I don't even, again, I might be making a big deal out of nothing right now. Okay, I'll stop. So pi over 6 is 30. How do we get 45? We already did that. Pi divided by 4 is 45 degrees. How do I get 60? What do I divide 180 by to get 60? 3. So pi thirds is 60 degrees. Right, and of course we already did 90. Pi divided by 2 is 90, 11. So let me throw something at you. Let's say I want to know what the sine of 5 pi over 6. I want to know what that is. What is in radians here? Pi. And this is 0. This is pi over 2. What's this?
2.
Yeah. No pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2. Is that cool? Every fourth of a way is pi over 2. You guys kind of with me? Not really. I didn't need that down there, but I just thought I'd throw that in. Can anyone tell me what quadrant 5 pi over 6 is in? How do you know it's in the second quadrant?
It's not a full pi.
It's not a full pi. But it's definitely more than this. So it's in between there, closer to this. That's 5 pi over 6. Can you guys see what the reference angle would be?
30.
And how do you think about it? No. I'm not talking about degrees up here. I'm talking about radians. So what's the reference angle in the units I'm using? Pi over 6. Good. It's 1/6 of a pi short of a full pi, which is a weird insult. That guy's 1/6 of a pi short. It's better insults. You guys semi with me? I need you to be able to see this because we're at the point, you guys are at the point, if I said 150 degrees, the reference angle is easy. It's 30 away from 180, whoop-de-doo. Radians, some new shit. We're not used to it yet. I'm trying to show you how to get reference angles when everything is in radians. You should not have to convert to degrees to do it. It's still the same thing. How short am I from a full pi, or how much did it go past? Or from over here, it's related to 0 or 2 pi. So this reference angle would be pi over 6, because I'm 1/6 of a pi short of a full pi. Okay. Now, you know that represents what angle? Now come at me with the degrees. In degrees, what angle? Huh?
180 degrees.
Pi is 180. What's pi over 6?
30 degrees.
30. No. 5 pi over 6 is 150. Pi over 6, that's the reference angle, that's 30. And what's the sine of 30 degrees?
1/2.
1/2. How did you know it was 1/2?
30, 60, 90, trying.
30 is close to the x-axis, sine likes y, sine doesn't like it down here, it's going to be the smaller one, it's 1/2. Is that alright? So it's okay right now if you convert that reference angle back to degrees, because that's how you have it memorized, and if you do enough of these, you'll start to memorize the radian stuff too. Let me stop for a minute. Is everybody semi-decent at the moment?
So one of the things for today is that you just want us to memorize equal radians and understand them?
Couple things. You need to be able to convert between degrees and radians, right? That's one thing. You need to be able to find reference angles staying in radians. And then I'm okay if you kind of think about what the degrees would be when you get the reference angle. This would be 30 degrees, so then you can do this based on what you have memorized. And I'm hoping if you do enough of those, you'll start to memorize sine of pi over 6 is 1/2, blah, blah, blah. Yeah.
Would you have coterminal angles in,
Oh, hell yeah, dude. So real quick, I'm glad you brought that up. If I had 72 degrees, how do I find a coterminal angle with
Plus
that?
or minus 360.
I would add or subtract so many 360s, right? So one way to do it is to add 360 to it, right? And then I get 432, neato. If I have 5 pi over 6, what do I add to it to get a coterminal angle?
2 pi.
2 pi, because a full rotation is 2 pi. Why do I add 360? Because a full rotation gets me back to wherever the hell I was. The idea doesn't change. I still add a full rotation or subtract multiples if I want to, right? You guys semi with me? That idea doesn't change. Just what represents a full rotation now in radians, 2 pi, not 360. Does it make sense? So the idea doesn't change. Yes?
So for 5 pi over 6 plus 2 pi, could you simplify the 2 pi and make it?
Yeah. So now if I wanted to keep going, how do I add these together?
Multiply the second.
Yeah, I need this one to have the same denominator, so I'm going to multiply by
Times 6 times
6.
6.
So I got 5 pi plus 12 pi over 6 makes
17.
17 pi over 6. Okay.
That's a lot of pi.
Yummy. Well, it depends on the pie.
Yeah.
You guys kind of with me? So yeah, so that's one thing that's a little sucky compared to degrees, is that you get a bunch of fractions, so you gotta make like denominators. Okay. All right. Let me ask you this: if you saw 33 pi over 4. That's a lot of rotations on top of a what angle in degrees? What angle is that related to?
45.
It's related to a 45-degree angle. How do I know that? Because it's over 4. So it's a multiple of pi over 4. You guys kind of with me? So if it almost doesn't matter what the top number is. If it's reduced and the bottom number is 6, that's going to be some kind of 30 degrees, right? Well, I got to be careful because you can reduce that. There we go. Well, you can reduce that. If it's reduced, there, that'll work. Some kind of 30 degrees. Does that make sense? No?
No.
What's pi over 6?
30 degrees.
30 degrees. If I multiply this by 11, right?
Mm.
That's still going to be related to some kind of 30 degrees. Does that make so if I
say that it will just be another angle, but we're
yeah, let's figure out what is 11 pi over 6. What is that in degrees? I just replaced pi with, I almost gave it away there. If I want to change this to degrees, what would I change? What would I put here? What's pi? In degrees.
180 degrees.
180. Right? You guys with me? Help me out. What is this? 330. You can do it, John. What's the reference angle for 330?
30 degrees.
30 degrees. All right. So I'm trying to give you a little bit of a shortcut to know ahead of time what's going to happen. If it's reduced and the bottom is 6, it's related to 30 degrees. What do I mean by that? I mean it's going to have a reference angle of 30. Do I know which quadrant it's in? No. It depends on how many freaking rotations they threw at me. You guys kind of with me so far?
Yes.
If it's over 2, that's related to 90 degrees, because 90 is pi over 2. Now, why do I say it's got to be reduced? Because if I saw, you could do it, Jeff. Look at you go. If I saw 15 pi over 6, is that reduced? No. How do I reduce that?
Subtract.
Divided by 3. Don't subtract shit. Right? So divided by 3, what do I get? 5 pi over 2. What kind of reference angle will that have? 90, because it's over 2. It's 5 times 90 degrees. Right? So I'm going to have a reference angle of 90. You guys at all? Again, is that really like an important thing to know? If you didn't know what I just said, are you going to be no, you don't have to know what I just said, but it's a beautiful little thing to know ahead of time. If I've reduced it and I see a 2, that's related to 90. If I see a 6, that's related to 30. I kind of know that ahead of time. Yeah.
Wouldn't we have to subtract 4 from that? Because that's a rotation.
Oh, sure. Then you talk about the rotations, but I'm not talking about that right now. I'm talking about, I know ahead of time this is going to be some kind of 90 degrees. Yeah. Yeah.
So you had 15 pi over 6 equals. So you just reduce that, right?
Reduce, yeah, exactly.
Oh,
If it's reduced, I can kind of know ahead of time what kind of reference angle I'm gonna have. Yeah, yeah, okay, okay. Alright, so let me ask you this question. Take a minute to figure this out. Do not convert to degrees too early. What do you got, Jeff? I don't even know. Sure, we'll do that. Is that more or less than a full pi?
More.
Is it a lot more or just a little bit more?
Just a little bit more.
So what quadrant is it gonna be in?
Three.
Third.
Does everybody understand that logic we just employed? I went a little bit more than a full pi. A full pi, you can see from your perspective, it's over here. Full pi is here, and I went a little bit more. In fact, you guys can see exactly how much more I went, correct? I went to pi, and then I went further. How much more?
Pi over 6.
Pi over 6? Because it's pi over 6 more than a full pi. Do you guys see that? So again, reference angles with degrees are easier because we've used 180 degrees and 50 degrees. We haven't used radians as much. So surely if I try to start teaching you guys metric, maybe some of you guys know it already because you came from a more rational country. I don't know, it's possible. We're the one country left of the earth, by the way, using a system developed by how big the King of England's foot was. Anyway, sorry. Nothing weird about that. We're fine. We're all fine. So what would this be? So what angle is this related to in degrees?
30
30. What's more important is, do you see how I know it's close to the x-axis just because I know it's only 1/6 of a pi away, which is really all I need to know for cosine. So it must be, cosine likes x. So it's going to be the bigger option, right? Because it likes it there. But it's going to be negative, right? So it's going to be negative. Rad 3.
Rad 3 over 2.
2. I love it. I love it. So sure, I understand. Just like when you learn a new language, you're not speaking fluently, you're translating as you go, correct? So radians, new language. I understand you're going to translate to degrees, but I need you to try to stay in the radians as much as you can before you go to degrees so you get more used to the radians. Right? I remember taking French in high school, and I had one of those teachers that only spoke French because their philosophy was, you'll learn French if I only speak French. And the only thing I remember is fermez la bouche. Fermez la bouche. Does anyone know what that means? Shut your mouth. Because we were unruly. We heard that a lot. We all knew fermez la bouche. We knew that. Sort of like omelette du fromage. Omelette du fromage. Cheese on. All right. Okay. So you notice that radians doesn't add anything fundamentally new to figuring out trig functions. They just tell me another name for an angle. You guys semi with me? But the thing that radians holds over degrees is that they are a truly physical measurement. They're not made up. Degrees totally made up. Right? So here's where radians really shines. Let's say I have a circle, a little circle, and let's say its radius is 10 feet. And let's say that I go through an angle of pi over 3. And I am curious about how long that side is. And this one we officially call this an arc length. It's how long that part of the arc of the circle is. So math people being creative, we say, oh, arc length. Is that all right so far? So, how the hell would I figure that out? You're like, I don't know, man. What do you want from me? So let me ask you this. Let's kind of build up on this. If I have this circle and it's got a radius of 10 feet, what's the circumference of the whole damn thing?
2 pi.
Yeah. Well, no. Nope. What's the circumference formula?
2 pi r.
2 pi r. So if I ask you how many radians would I go through? 2 pi. If I ask you how long of a trek that would be, that's the circumference, 2 pi times the radius, right? All right, so what would it be? 2 pi times 10, so that would be 20 pi. Is that cool? 20 pi! 20 pi! Sorry, I just went a little crazy there. Now, if I want to know how much is this piece, isn't that a fractional part of the whole thing?
Mm-hmm.
Now just go with me for a second. We're going to get a shortcut here in a minute, right? So, what fractional part of the whole thing is this?
1/6.
Why would it be 1/6?
Because the reference angle of 3 refers to 60 degrees, and 60 times 6 is
360, okay, so
360, yeah.
6 of these, 6 pi over 3's makes what? What's 6 times pi over 3? 2 pi.
2 pi.
Oh, I like it. So isn't this 1/6 of the whole way around, which in this case was 20 pi? Yes?
So, could you have done pi over 3 divided by 2 pi to get pi over 6, and then you multiply?
We're going to get there, don't worry. Okay. All right, I want to stop for a second. So I want to do it this way at first, because it's a very physical idea. I'm slicing a piece of the pie, correct? So of course, this part of it is going to be some fractional part of the whole damn thing, right? Pi over 3 is 1/6 of 2 pi, right? Okay, in fact, if I write this, I'm giving us concrete numbers just so we can kind of latch onto them, but let me write it like this. Wouldn't it be whatever the hell the r is, wouldn't it just be 1/6 of the whole way around? Yes? And how do you reduce this? You'll get 2 pi over 6 times r. How do you reduce this?
1/3.
Pi over 3 times r. Isn't that just pi over 3 times the radius? Do you guys see that? Do you guys see that?
Mm-hmm.
And on one level, this needs to make nothing but sense. If I go all the way around, that's the full 2 pi. If I went halfway around, wouldn't it be half of that? Wouldn't it be pi times r? But what's pi? Isn't pi this angle in radians? So what's the shortcut then to find the arc length given any angle in radians and radius is just to multiply the two together. The arc length formula is too kick-ass to believe. It is simply, let me write it down up here. Get rid of a lot of this stuff here. The arc length formula is simply r times theta. And I need, now another way to look at this. What does a radian represent? It's the radius length walked along the circle, correct? So let me ask you this. If I went, if the radius is 10 feet, and I go half a radian, remind me, a radian is the length of a radius, correct? 1 radian is exactly 1 radius. So what would half a radian be here then? I would have walked 5 feet. Does that make sense? So didn't I just take the radian measure times r? I took r times the angle. Yes?
Would there ever be an instance where you're not given like the radius?
Say again?
Would there ever be an instance where you're not given the radius?
Only if they're doing some silly algebra thing where the arc length is this and the angle is this. What's the radius? And then you can solve for r, correct? I must know 2 of those 3 variables to use this. Does that make sense? Yeah. If they only gave me 1 variable out of 3, then screw them. That's mean. Is that cool? So, but they could do the algebra thing and say, I got a circle and I go pi over 4 and the what am I trying to say? And the arc length I go is 12 feet. What is the r? So now I got to solve for r. Is that all right? Just divide and solve for r, is that okay? So they give me any two of these variables, I can solve for the third one. Is that all right? I can't remember, they might do that, but I can't, off the top of my head, I can't remember if they do that to you. Let me stop for a minute, is that okay? I mean, on one level, this is just a silly little formula, and if I tell you two of these, you can figure out the third one, correct? So they could give you a problem like that, sure. Okay, okay. Notice, if I have angle in degrees, it ain't gonna work. That's bullshit. One reason is radians mean number of radii, correct? So of course, if I have 2 radians, that's 2 radii, 2 times the radius makes sense. This much times the radius. Degrees, what do they mean? What does a degree mean? 1/3/600th of a circle, just arbitrarily, correct? We just arbitrarily picked it. So what if we would have picked 620, 720, or 400, or whatever? That would totally change this arc length. But the arc length should be a number. It shouldn't change depending on what unit I want to use. So here's what I said earlier when we first started talking about radians. If I have a trig function of an angle, it does not matter if it's in degrees, if it's in radians, if it's freaking a picture, right? I could do any of those. It could be in anything as long as I know what angle it's referencing. So does 45 degrees reference a different angle than pi over 4 radians? No. They reference the same angle, correct? If the angle is not inside of a trig function, it has to be a real physical number, physical measurement. And what's the only angle measurement we have that's a physical measurement? Radians. Yeah. Yes.
You keep saying like, okay, maybe I'm understanding it like this. You say the radians represents the angle, the physical measurement of an angle, right? But then the curvature is how you're measuring the curvature, the arc length, in terms of radians.
Yep.
So what would the angle be in terms of?
So here's the idea. Let me write this a little better. So if this is 10 feet, and I go through an angle of 1/2 of a radian.
So that represented the angle, that didn't represent
Yeah.
the arc. Okay,
I just kind of, because I put 10 where I did, I had to put it outside. So that's my
okay,
fault.
so radians is like
Radians is angles.
angle.
But they are related to how big the radius is.
Mm-hmm.
So again, if I rotate through what is half of a radius, that exactly means I've gone half of a radian angle. I've gone half of a radius worth of distance along the circle. Right? And if the circle was bigger, it would still represent half of a radius, just of the bigger radius now. So that's why it kind of always works out. Because if I make the circle bigger, the radius gets bigger. Okay, maybe. So let's try an example. So now we have this formula, S equals R theta. We like S for position for some reason. I think it's related to a word in a different language. Like, real quick, do you guys know why we use M for slope? Y equals mx plus b? This is not completely confirmed, but it makes sense to me. M is like in French, marcher means to walk. And slope is kind of like how you walk to get around something. You go up and down and up and down. So they think that it's because M for marcher. Did you guys care about that? No. Sorry. But I'm just trying to help. Why the hell did we use the letter S for arc length? I can't remember. I don't know if I ever really looked it up. Because we use S for position in physics in a lot of places. So just to let you know, it's just something we do. So now we know S equals R theta. What must be true about theta before you use this formula?
Has to be in radians.
Must be in radians. Because radians is not made up bullshit. Radians is an actual physical measurement. So here's an example problem. Let's say I have a circle, radius 110 meters, and I walk through an angle of, what do you got, Jeff? 80 degrees along the outside of the circle. How far did I walk? So this is the math teacher's favorite kind of problem, multi-step problem. I might have just given something away, but can I just do 110 times 80?
No,
Why not?
because it's in degrees, not.
Because it's for freaking degrees, exactly. I love it. So I want to use this formula, but I know that this must be in radians, so what's the very first thing I have to do?
Convert.
Convert, yeah. So take a minute and figure out this problem. I'll stand up here and watch it. There we go. Yeah, okay. Okay, where's that? There it is, okay, good. So first step is get the angle into radians. So how do I do that?
Times 1 pi over 1.
Yeah, so I want to kill degrees, so put it down there. I want to go to rads. So pi radians in 180. Now this is one place, whenever we have a word problem, so if I said, how far from the school do you live? And you said 11 pi over 3 miles. So what the shit are you on? Right? So this, whenever I have a word problem, that's where I'm going to actually multiply by pi in the calculator. Right? Get a nice decimal answer so we all look like we're humans. So I can reduce this. I'm going to throw this in the calculator, almost doesn't matter, but what is this? If you reduce this all the way, what do you get?
4 9.
Yeah, so it's 4 pi over 9 radians. So now I'm not allowed to use the formula.
Mm-hmm.
Yes. So S equals R
110
times theta. And now you can just throw all that shit in the calculator. So does everybody know where your pi button is, whatever kind of calculator you've got? Do you know where your pi, do not use 3.14. That is bullshit. Bullshit. If you don't know where your pi button is, let me know. Or just, you know, that's just the way it's going to be for me. No, stop. Just let me know. It's not a big deal. If you don't have a calculator, I'm sorry, I didn't bring it. It's too bad. So don't say anything yet. That's interesting.
Would we have to report that to one significant figure?
Again, significant figures, okay. Yeah. Yeah, that would have just added a whole other layer. It's not really that necessary. So what do you guys get for this? Putting all this stuff in your calculator?
153.5.
What? Sorry?
153.5.
Yeah.
889.
I know it's going to be around 150. 153 point. Sorry.
588.
588. So I would tell you on the test what to round it to. Is this good?
Not yet.
There it is. Please don't make me be more a dork than I am. If you don't put units, I'm going to go sheep. Light years. So just don't make me do that. That's really. I'm sorry. Is that how you guys doing there? Is that all right? So the formula. You all right? The formula uses the idea of radian directly. The radian is the number of radii that I've gone. So if I just multiply by how big each radius, then I will see how far I went. That's the basic idea behind this formula, is That, if it's in radians, is the number of radii I went, times how big each radius is how far I freaking went. That's what the formula really gets at. Does that make more sense? Physically, it just, that's why this must be in radians, because then it actually means that. Yeah.
Can you give us an example where we solve for the radians?
Yeah, I mean, it's kind of funny. I love algebra, but this is kind of boring with it. So they're going to say something like this. You go through an angle of pi over 7 radians. The length, the arc length is 400 feet. What's the radius?
No, not like solve for like the angle.
Solve for the angle. Oh, I'm sorry. You want to solve for what? Sorry?
The angle.
You want to solve for the angle. Okay, so I walk through the valley. No, I walk through. I walk 50 meters around a circle of radius 12 meters. What angle did I go through? What angle did I kind of trace out? S equals r theta. What's S?
50.
Because this is how far I went, correct? S is the arc length, how far I went. What else do I know?
The radius.
Radius. Right? And then how do you figure out the angle? Divide. Yeah, divide by 12. Yeah.
I solved this in a completely different way, and can I ask you if it's a good way to solve it? Because, yeah.
The problem I just wrote? Or
No,
that one?
that one.
Okay, I was going to say, how'd you do it?
I instead of doing whatever the heck you did, I multiplied 110 by 2 because 110 is the radius, and you multiply it by 2 to get 220 pi. I divided 3.
Oh, okay, sure.
Right.
You did all the way, you basically did all the work we did to get to this equation. So personally, I'd rather use this because this is the simplified version of all the work you're doing. You are doing what we did to create this equation. Yeah, does that make sense? I mean, that's the first example I did. I did a fractional part of the whole circumference. So do you have to do all the work? No. Is that work wrong? No. Are you going to take more time doing it than you should? Yeah. Does that make sense? Okay. I want you to understand, nothing wrong with that work. Tears. But this is more efficient. This is the result of every possible problem that you could do that way. This is the result. So I can just throw shit in there and see the answer immediately instead of all the extra little steps. Does that make more sense? Okay. Yeah.
On the problem to the left, would you make us divide by pi also to put it in terms of?
Where's pi?
It's like once you just.
So if I divide by 12,
Yeah.
it's interesting the answer, the question you just asked me, and then whatever that is if you throw it in the calculator. When I use this, in order to use this equation, what must be true about the angle?
It's in radians.
If I use this equation to solve for an angle, what will it be in? Done. So what the answer I get has pi in it already. It's like it's
Yes.
already been, so what is 50 divided by 12? 20, good, 25.6, which is 4.66, yeah. We'll just call it 4.17 radians. That's what it is.
Do we have to put our calculator in radians? Or
No. For this,
yeah.
no. Let me explain why you have to put your calculator in. You ready? You ready? Okay, this is a good, I love it. It's almost like I put you there, just to keep me on track. Because I do apologize if I ever go down a few rabbit holes. So I love it. Okay, this is a beautiful question. Here. Could you guys, real quick, right now, what's the tangent of 17.2 degrees? Can you do that if you have your calculator? Can you tell me what that is?
Or 0.309, so 0.31.
0.3?
3-1.
1? Okay. Roughly? Okay.
Yeah.
So rough. Okay. Now, what is the tangent of 17.2? Do you understand that's a different problem?
Oh,
How is it different?
Not degrees.
It's not degrees, it must be radians. If I don't put degrees, it's radians. So you need to put the calculator into radians so it understands 17.2 is radians.
Got it. Okay.
When you do this, I don't give a shit what mode your calculator's in because 50 divided by 12 is 4.17. I don't care what you put it in.
Right. Okay.
I'm not, the angle is unknown. Now I know it. Now if I wanted to take the cosine of this, I have to tell the calculator radians.
Got it. Okay.
Because it doesn't know. And when you put 17.2, doesn't it look like that in your calculator?
Mhm.
So I have to put it in degree mode if it's degrees, or radian mode if it isn't, because the calculator has no freaking idea what the number is. It's just, that's a number, help me out. Does that make sense?
Mhm.
Good question. I don't want to make it sound like, it was a beautiful question. Okay. All right. Man, this is working. Whoa. Feels a little high. The old ones are good. The ones these are low odor. The other ones, dude, you can get hot pretty quick. All right. Is everybody with this to a certain degree? I mean, this is relatively new still. You gotta play with it, but the formula's nice. S equals R theta. That kicks so much ass. So, here's the next thing after that. If I slice a piece of pie, I can ask about how long the crust is, or think about pizza. I can ask about how long the crust is, right? The more interesting question for me would be, how much freaking area is that? How much actual pizza am I going to shove into my mouth in a minute? You guys kind of with me? Now I want freaking pizza. Sorry, everybody. I'm going to erase all this. You ready? Okay. Man. Well, Jeff, you can get pizza. It's all right. Just got to work out a little bit more. It'll be all right. Okay. So coming back to my cutting a piece of pie or pizza or whatever, so let me do it like this, just because I'm going to slice a piece like this. That's the angle, and the radius is R. How long is this? I didn't give you any numbers, so just
Theta times
R theta, I love it. Is everybody with me? Now, the book explains this in a different way, which I don't blame them. So you can look in the book for the boring ass way to explain this formula. I prefer this way, which is really freaking cool. Let me take this slice over here. Here's the slice we're talking about, right? This is R theta, this is R. What is it? What shape does it almost look like? Triangle, right? The one problem is it's curved on one side. You with me?
Yeah.
Okay. But what's really cool is if I made this really small slice, let me see if you guys understand this. By the way, do you know that there are people that still exist that think the earth is flat?
Yeah.
If you are one of those people, please keep it to yourself. At least you're in the right place. It's got to be okay. Why do people believe the earth is flat? Why does it look like it's flat? It does. I will agree. It looks like it's flat. Why? How big is the circle of the earth that measures the curvature? It's freaking big. So if I have a circle and I zoom in on it, and I zoom even more in on it, it's going to look flat. If I zoom in right there, it's going to look flat. You guys understand? The more I look at it, the more it kind of uncurves as it comes in close. Are you guys with me? So, if I made this slice, if I had made it really, really thin, this side would have been essentially straight across. You guys kind of with me? And then the idea is I can add a bunch of these triangles to get the whole thing. So watch this. This is kind of cool. This works. And the book does it a different way. I wanted the area of this, and I'm going to pretend like it's a triangle, because if the smaller this is, the flatter the side would be. I'm going to pretend like it's a triangle. What is the area of a triangle in general?
1/2 base times.
Good, because if I have a parallelogram, the area of this is height times base, and any triangle is half of a parallelogram. Whoop-de-doo, right? That's why. What is the base? Pretend like the bottom is flat. What is the base of my triangle? What's the bottom if I pretend like it's flat? R theta, right? What's the height?
R.
R. So you got 1/2 R squared theta. That is the formula for the sector, the area of a sector. There's another way to do it where I do it sort of like how we developed R theta. I say, what's the area of a whole circle? Oh, let me show you this, by the way. I'm kind of happy I remember this. Do you guys, all right, first off, what is the area of a circle of radius R? Do you know? Please tell me somebody knows. What's the area of a circle?
R squared pi.
Do it again, sorry.
R squared pi.
All right, pi R squared, okay. Does that sound familiar? Real quick, does anyone know why? Because you're like, pi around squared. That's the old stupid joke. So watch this. All right, let me show you. This is too cool. And again, that could be too strong of a word, but we'll see. Just for a minute, I gotta show you this. Can you imagine that I slice this circle in half? I cut it in half, right? I have a circle out of construction paper and I chop. And then what I do is I go, from the center I go out. But I don't cut through the outside. Are you guys kind of with me? So I cut it in half, and then I go out to the top, but I don't cut all the way through. So I can pick it up and put it down here. Are you guys kind of with me? If I open this up and put it, do you see? Couldn't I do the same thing to the bottom? Open it up, fit it in. What shape did I just kind of make?
A rectangle.
Good. The R is basically the height of it. Especially if I made my triangles really small, right? And what is this? Real quick, what is all the way around the circle? 2 pi R. That's the distance. Yes, not the angle, the distance. So this, what is it? This came from this, yes? What is that? Pi R. So this is pi R. So what's the area of that rectangle? Pi R times R, pi R squared. Yeah. So any area that we don't know, we can slice it and reposition it. We can reorient, because by slicing it, putting it back together, I'm not making or losing any area. I'm just reorganizing the area. You guys semi with me? Right. That's a little side note. Nothing you have to know necessarily, but I just want more people to see that. Yes. Okay. So I could have, instead of doing what I did here, I could do what the book does, which is the area of a circle is pi r squared. So if I want to know a piece of it, I can just see what fractional part of pi r squared it is. Blah, 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 shackety schmackety, bunch of crap. Yeah.
So for the area of the triangle that we had up there, it was half r, 1/2 times r squared times theta, right?
Yeah, so the area is 1/2 r squared theta. Yes.
Couldn't you also rewrite it as 1/2 times s, which would be the arc length?
Ooh, look at you. All right, so S is r theta.
Mhm.
So you're saying I can make area equal to what?
1/2 times s times theta
No, times r.
times r, that's right.
Now, real quick. Dear God, you don't have to do this. I love that you saw that. It's beautiful. Is this necessarily the most helpful thing? Not necessarily, but it's kind of cool because I'm almost always going to ask you for arc length and I'm going to ask you for areas, and then you just throw that in there. Do you have to know this formula? No, you don't. Okay. You must know this formula and you must know this formula for sure. Whatever the hell you do with them after that, you can do whatever the hell you want to. Yeah. But that's a good observation. I love it. Okay. Time to go. Oh, we got time. It's amazing. You're all like, damn, he's got time. So, let me give you an example. And again, is the angle out in the wild, is it captured by a trig function, or is it out in the wild? Is the angle in this formula in a trig function? Is there any trig function in this formula? So is the angle inside of a trig function?
No.
No. Therefore, it must be in what units? Radians. If it's inside of a trig function, it doesn't even have to be a number. It could be a picture. I just have to know what angle you're referencing. If it's outside, it must be radians because that's physical measurement. Yeah.
So, when you said, earlier you said one half times, r theta times r, that equals pi, one half, r squared theta. Is that, when I was thinking about it just now?
Yeah.
I was distributing the r type of thing?
There's no distribution if there's no addition.
Oh, okay.
Yeah, I always get somebody that's like if I said what's 2 times 3 times 4, and I said it's 6 times 8, I would hope you'd look at me funny.
Yeah.
Because there's only one 2. How the shit does both of these get a 2 when there's only one of them?
Yeah.
So you only distribute if there's a plus, then it distributes, right? Okay. Alright, so let's try to use this formula. Here's a circle. Wow! The radius, we're telling you this is a circle. The radius is, what you got, Jeff? 7.39 inches. And I want to know if I go through an angle of, what you got, Jeff? I don't know, man. Let's go, blah, blah, blah. Oh, let's just do, give me a second. Yeah, sure. Let's say I go through an angle of 3.97 radians. So I want to know the area of this sector. The area of this. This is Jeff being an asshole saying, I'll take one slice of the pie. Chop, chop. This is my slice. Thank you very much. So what do you need to know for the formula? You know the
It
radius.
would be,
Do we know the radius?
Yeah.
Yes.
it's 7.39.
You need to know the angle in radians. Do we know the angle in radians?
3.97.
Yes. This came up earlier. Does everybody understand? Pi doesn't have to be present. 3.97, somebody multiplied the pi in. That's why I don't see pi. Pi doesn't make something radians. In fact, one of the most evil questions I could ask you would be, what is sine of pi degrees? That is not radians, that is degrees. You agree? That would be evil.
So would that be sine of 3.14 degrees? Like something like
Well, 3.141596, yeah. So I just put my calculator in degrees, and I would put sine of pi, and it would know I meant degrees. But you see how that's evil? Because right now, you guys think pi means radians. No, gotta be careful. No degrees means radians. So when I say 3.97, I didn't even have to put that there, but I was being nice. That would be radians. Doesn't need a pi to be radians. Somebody multiply the pi in and then round it.
No.
So, yeah, that's all you gotta do, right? Just throw that all in there. So whatever the hell that is. I don't know. 100 something makes sense. 108? 41? What would the units be?
Inches.
No.
Inches squared.
Yeah, square inches. What units are these?
Inches.
Didn't I square them?
Yeah.
Anytime you have area, I've got to cover it, so I've got to go in 2 dimensions, which means it'll be squared. Volume includes a 3rd dimension that's always cubed. Yeah.
There isn't any like specific bullshit like there is with degrees, like how like minutes and seconds, right?
Oh, the beautiful thing about radians is no, because radians are always in decimals. Or if they're going to be something without pi, they could be in decimals, yeah. Does it make sense? Yeah. I kind of agree. It can be a little bullshitty, but they exist, so it's good to know. And again, that's another thing that it has over degrees. Degrees is made of bullshit, and then, hey, look at the stuff we made for ourselves. Go us. Go Team Human. Okay. Okay. So, a lot of the problems, this is, by the way, this is section 3.2. But a lot of the problems in 3.2 is just plug and chug. You've got to first make sure the angle they give you is in radians, so part of the problem could be conversion, right? I think they do that to you somewhere? Maybe, no. Maybe, no, yes, they do, they do figure a few times, okay. I like it. So, here, we basically just finished section 3.2. Section 3.3, let me give you this. This, unfortunately, I didn't realize this. I had printed this out for a workshop I did, and as you can tell, I didn't get a very good attendance, which is fine with me, because, but one side of this talks about something exceptionally freaky. It talks about vectors, which is in our future, actually. But please, dear God, don't worry about the side that talks about vectors. Are you with me? I just have copies, and the other side is more important. So let me give that to you. So you worry about the side that's got pictures and colors. Don't worry about the side that's got no pictures and vectors. Okay. Alright, let's take a look at this real quick. So, a little bit of this is in our future, but I didn't see any real problem with throwing this at you. Some of this is in our past, too, so this is just sort of a interesting, out of time kind of handout. But no. Am I even focused? Something very useful about this is this, of course. Now, dear God, you do not have to memorize this or something. I am not going to give you a blank unit circle and make you fill that shit in. That is so much bullshit. Because again, how much of the circle do we even concern ourselves with? The first quadrant. So why would I make you fill the whole damn thing stupid, right? Now, real quick, what is cosine like?
X.
What is sine like?
Y.
So if you notice, the x piece is the cosine, the y piece is the sine. It makes sense, right? And you can see if I drew a rectangle, I love it. What am I teaching? If I drew a triangle, this height keeps getting bigger, which of course corresponds to the y piece getting bigger, which corresponds to the sine getting bigger as you go through. Does that make sense?
Yes.
So this is a nice visual. It also has the radians on there, which I thought would be a good reference to use as you do radian stuff. You can kind of reference this. It's really nice. Every 6 over 6 is related to a 30 degree. You see that? Every 4 is 45 degree. Every 3 is 60 degree. Just like I said earlier, right? Blah, blah, blah. Okay. By the way, 2 pi is 6 pi over 3. Is that cool?
Mm-hmm.
So you see how 5 pi over 3 makes sense? If this is 6 pi over 3, 1/3 of a pi before that would be 5 pi over 3. Do you guys see what I mean? So if you 7 pi over 6, I went how far past pi? How much of a pi more than pi is 7 pi over 6? It's pi over 6 more. Because what's pi? Isn't pi 6 pi over 6? Pi is also 3 pi over 3, so 1/3 more of a pi would be 4 pi over 3. Okay, so if I look at this, oh, why'd that block? Shoot. 2 pi is 6 pi over 3, so 5 pi over 3 makes sense because it's not quite a full 6 pi over 3. 2 pi is what over 4? No, 2 pi is what over 4?
8 over
8 pi over 4. So 7 pi over 4 is 1/4 of a pi. You guys see what I'm saying?
Yeah.
So you can kind of get reference angles by making like denominators. And going from there. Okay, maybe. So this will be good to have sit next to you when you're doing the radian section of work. Section 3.3 does not throw anything really new at us. Let me make sure, yes, nothing new. Nothing new. Nothing new. Nothing. It just redoes everything we've done already with angles, but now they're in radians. So it's basically like the problem I was doing earlier when we did, I can't remember a specific example, like 3 pi over 4. We did tangent of 3 pi over 4, something like that. So you already know what tangent of 45 degrees is. You're supposed to, you know how to find reference angles. You know what that is. Now you're doing the same work, but now you're just doing it in radians. You already know the answers if you can just get used to what the radian angles are telling you. Does that make sense? So 3-3, there's very little new in 3-3. It's just doing all the same shit we did before, but now radians. So it's another way just to get more used to radians is realizing they lead to the same answers. So for example, what is the cosine of 7 pi over 6? When you look at this, this is easy because the answer is sitting right here for us. What's cosine of 7 pi over 6? Negative rad 3 over 2 because cosine's the x piece, right? You guys kind of with me? A little bit?
Yeah.
Okay.
Yeah.
Let me make sure. I'm pretty sure. I don't think there's anything new. No. No. Okay. Yeah, that's all right. We'll get there eventually. Okay. Nothing really new in section 3.3. I think, let's do this. Nobody here is going to worry about it. Let's go ahead and call it for today. What do you guys think? End of class. End of class. It's good to be the teacher because then I let myself out early too. It's amazing. I got a lot of shit to grade, so I'll let myself out early. All right, guys. Let me know if you have any questions. Otherwise, I will see you. What is today? Wednesday? I'll see you next week.